Okay, this is a tutorial on how to make a cavemanish lightsat launcher in RP-1. First thing you need is a science core avionics that we're gonna put on top. By this time, when you're doing lightsats, you are gonna have avionics prototypes, probably, or you might even have early avionics, but we're gonna go with the avionics prototypes for now because it's sort of it's not a requirement, but you'll need this eventually to even do the program in the first place entirely. Let's put a smooth cone on top so it's a little bit aerodynamic, and that way we don't need a payload fairing, and a payload fairing is heavy, and this way we don't need it. Yeah, this is about fine. This is not optimal, but it doesn't matter, right? You could put experiments on there, you could put other things on there. Some cases you might need a solar satellite, in which case the easiest way to do this is to upgrade from avionics prototypes to early avionics, because the power drain goes from 25 watts to a fraction of a watt, which means that what you can do is you can just put a couple tiny solar panels on the back, and then when you launch, when the sun is behind you and you spin it up, then it'll just stay solar powered for long enough to complete the program. Okay, anyway, we need a fuel tank, we need an engine. We're going to go with the American ones for no particular reason. The Russian U-2000 is perfectly adequate for this too. And by this time you have basic rocketry for this design, so you also have stringer tanks. Make sure you use high pressure tanks. This is our final stage. Our final stage is going to go on 0.5 meter diameter. And what you can do for this design is you can put a mount on there that makes it cover the engine, which makes it more aerodynamic. We need a interstage, and then we need, of course, we need a second B, right? One B is not going to cut it. We need probably at least 2. You might need more, you might need 3 or even 4. Every B, of course, adds complexity. It can fail and it makes it more risky, but it also might make it lighter, better. You know, it's there's a lot of flexibility in that design process. The hollow interstages, right? This one doesn't need to be this big. This one is 0.5 meter diameter, and it can be as short as it wants. This one we can make the fairing, the shroud a little bit longer, not that long. The burn time now is, we can make it a little bit longer. It is now 22 seconds. That is fine. This one, what we're gonna do is we're gonna put a nose on there. That is the 2-to-1 long one, and then we also need the skirt so that it's a little bit more aerodynamic. No, we went past it probably. Yeah. So the small shroud for this one. This one is on 1 meter and then 0.5 meter. You could go any other diameter. It doesn't really matter. It is not specific. It is just that this one is you're gonna need to tool some diameters. You're gonna need to make some choices, and what you end up picking with is rather personal preference. It doesn't matter too much. This one, it can be a little bit shorter, and the way we're doing this is this is a rather efficient design. The skirts are massless in RP-1, so this way we are aerodynamic at no real cost for our payload budget. Our engine, this one is a WAC Corporal. We want it to be a AJ1027, which is higher thrust, and for this second stage rather than the third stage, the thrust doesn't matter. And this one, right, we also want to go with HP aluminum stringer tanks. And let's see our burn time. This one is 1 minute 52 seconds. This is a little bit long. We can make it shorter. It can burn for around a minute. Let's go with something like this. This looks fine. And then what you want is we need avionics to go underneath this, because then we need our controllable first stage. Because if we can't control it, you can't even complete the program because it requires control. So let's see. We're gonna go with around 24 tons. Around a little bit of EC. Oh, it doesn't fit yet. So 24 tons. Let's go with 500. It doesn't need to be this long. Let's go with something like this. How short can we make it? Oh, that short. So 24. Let's give it a little bit of EC to control. And then underneath this you can put your modular tank, and then the key that makes this all work, the XLR43, an amazing engine, you could say overpowered, because it is so much better than all its contemporaries. We'll fix the fuel later, but this is of course not too big of a tank. We can make this a stringer tank, because that's what we have. And you see there's 2 seconds of burn time. We'll deal with that later. The idea is this one will throw the above package on a suborbital trajectory, and it'll coast and then it'll burn. But in order to do that, it needs some control. So what we're going to do is we're going to take a fuel tank and we're going to make this real tiny. And of course we're going to go with the stringers tanks. It is HP, and it's yeah, it's going to be a small tank. We need some RCS. Let's go with well, any one of these will work. We can go with the modular one. Nope. And we want to use a decoupler, but we'll deal with that later. So first things first, modular RCS. There are multiple ways to do this. What I like to do is just put some of these under there. You need a little bit more control than that. The 3-way is usually fine, and then we need different kinds. This one is, oh yeah, this one is fine. It needs to be a little bit smaller. The idea is you want to have some pointing sideways to give you some control over your roll and such, and you want to have some pointing downwards to provide ullage later. These ones, they are right now on nitrogen. HTP is probably your best choice. These ones, they have combined around a kilonewton. That is more than enough. They could even be a little bit smaller. It's oh, I think I need a little bit bigger. Yeah. No, this is fine. This is fine. Okay. And then we put hollow interstage on there. This one was at 1.2 meters diameter. It doesn't need to be this big. It does need to fit underneath it. So something like this. And we of course need fuel for the modular RCS. And this modular RCS, it doesn't need to be activated until this decouples. Okay, so this is fine. We want to ignite our engine before we decouple. So the idea is now you ignite the main engine, then you loose the clamps. This one flies for a while, then at some point this decouples and the RCS activates, right? And then what you are left with is this whole package. This one will coast to apogee, and then it will spin up, provide ullage for the stage, ignite the engine here, decouple the stage, then it will ignite the top engine. Oh, the other one. So, oh, let's go to do this the right way. No, it's at one per. So this engine will ignite, then it will decouple, then the last engine will ignite, and then that will decouple. So that's gonna be fine. Okay, now let's fix this stage. Let's go with a 1.6 meter diameter, and what we'll do is we'll put a nose on there, because this is 1.2 meters and this is 1.6, so we go with the 4-3 version of the tank, and that makes it a little bit more smooth. For the mount, let's go with a boat tail. It's gonna be fine, except we messed up the color, but it is what it is. It's not gonna matter. Yeah, it's the color doesn't matter. I don't really care about that. And of course we need to have enough fuel in there. Right now it burns for 26 seconds. That is not long enough. This thing can burn for 65 seconds, and if you actually look at the engine, it also has a tested burn time of 200 seconds, which is very long, and it's gonna fail. The mean time between failure of that thing is like 4 to 5 minutes, so don't burn it for 3 minutes, but longer than a minute, it's gonna be fine, right? We can burn it a little bit longer than this. Let's go with something like this, and what we can do is let's go with 24 tons, so just a little bit less than this. Right, 1 minute 25, that's going to be fine. We have 9.5 kilometers per second of delta V. This is fine, but you might find that once you put some payload on this thing, because right now the payload is the avionics, which is fine for lightsats, but if you want to put something on this, you might need more than 2 Bs, or you might need to increase the burn time of the XLR 43. But let's give this one a test, see how it flies. How does this work? What settings do you use for the neck jet and such? And the idea here is, again, you fly guided on the first stage, and you coast, and then you provide a sort of a package with RCS control, controllable avionics, and your Bs and payload. Okay, so for this, remember, do not use classic ascent, use prime vector guidance. Classic ascent is for suborbital trajectories, prime vector guidance is for orbit. Our last stage is stage 0. Early shot of stages, we do not do that because we have no control on paper. And our unguided stages are 0 and 2, which are the top 2 Bs. We have a coast stage, and our coast stage is 4, and that is when the above package decouples. We do not have a fixed coast length, we do not know that will optimize. Yolage lead time 20 seconds, 10 seconds is fine. Spin up stage, we do our spin up manually because it's not always that broken. We have a very high SLT, right? A very high sea level thrust, so the booster pitch rate, this is probably not going to be good enough, right? So let's go with 1.5. We might even go 2. It's going to go very steep. Let's just go with 2 degrees per second. And our final flight path angle and burnout altitude is, let's aim for like a 200 kilometer or like a 180 kilometer orbit, because if you go too low, then it's going to go very low in the atmosphere, and remember that this is unguided, so this is also going to fly unguided through the atmosphere. It's not going to behave very nicely if you go too low in your burnout altitude. Of course, you need to go above 140, 150, but 180 should give us enough leeway. Okay, so let's see how this flies. The rest is all fine. It's going to pitch over quite fast, but we'll see how it does. You see, it gives us a coast time of around 198 seconds, so we'll see how this does. And our orbit, you see, it gives us an 8 megameter apoapse, but that's going to go down as it loses delta V to gravity, drag, you name it. And the beauty of prime vector guidance is that it will optimize descent for you, right? If you do this manually, you're not as good as the computer, right? In the pitch program, right now it's trying to pitch over. It might struggle a little bit to actually hit prime vector guidance if you don't pitch over fast enough, right? Then you need to change the Q alpha limit, but for now there's probably no need for that. We can go a little bit faster, time warp, see how it does. Okay, so it's now 27 kilometers altitude. We are flying at around 40 degrees, so this is gonna do perfectly fine. If you look at our orbit info, you'll see our apoapse is around 160 and it's rising, so this thing is pointing down a bit. What this means, once it does this aggressive of a maneuver, that you should probably pitch faster, but for our case the pitch rate means that our Q alpha should have been a little bit higher. What you can do also is boost the pitch rate 50 meters per second, change that to 25, but this probably it'll do fine. As of right now, our package, right, it decoupled, it activated the RCS, and it looks completely out of control, which is technically true, but yeah, it has enough RCS. It has way more than what we needed. We could have used 10% of this and it'll do fine, but it's regaining control because it's very high in the atmosphere. It's gonna point, remember, it still has another 2 minutes to point in the right direction. Point prograde. We could even time warp a little bit further. Right, so we're in the atmosphere still. We can physics time warp, make it go a little bit faster. You'll see the RCS firing, and then once we're around like 20 seconds out, we'll have to undertake some action, right? So like in 20 seconds, right, it wants to fire this B engine. it's going to provide ULIS for us, but it's not going to spin up. So what we do is we just hold E, and this will spin up our engine. We could have made our our RCS a little bit more powerful, so it will spin faster. We could have held E a little bit earlier, but this is probably going to do fine. Our spin is a little slow, but it's whatever. Right? Just make the RCS bigger, hold E earlier. It's whatever. This B is going to fire. It's going to fire for around a minute. This might fail. Also, the other one might fail, or the XLR43 might fail. But this is a cheap design. This will build reasonably fast, especially as it has the stringer tanks, which means that you also unlocked a faster engineers. Right? The engineer efficiency went up. So these ones, don't be surprised if they just end up building in 2-3 months. Right? You can launch multiple in a season, and yeah. So if they fail, don't feel too bad. These are cheap rockets. You can just launch another one. Every time the engine fails, it'll get more reliable. Okay, so the first B is almost done firing, and then it's gonna ignite the second B, and then it's gonna decouple. There we go. And this final one, it should hit orbit. As you can see, we are still going, even with this very slow spin rate, we're going very straight, and it's gonna get us into a nice orbit. We're almost there. We still have 1 kilometer per second of delta V. And there we go, there's the orbit sign. And this one, you see, it is considerable performance. Our apoapse is 3,000 kilometers, so this is way more than enough. You'll find that once you put some weight on this thing, that the delta V is going to drop, and you'll want to use a third B. Just add another one of these behind this one, and then you have 3 Bs instead of 2, and it'll fly further, higher, you name it. Right? So this is how you get to orbit with the lightsat launcher, and this is, it is very flexible. This is also the speedrun meta. It is very nice design. All right.